You know, the universe is never, ever still. Everything, from the electricity zipping through your phone to the planets spinning around the sun, is in a constant state of flux. But what if I told you there's a secret mathematical language, a language designed specifically to describe, predict, and even control all of this change? Well, that language is called differential equations, and today we're going to pull back the curtain and demystify it together.
Okay, let's start with a little puzzle. This right here is an RLC circuit. Looks simple, right? It's just a resistor, an inductor, and a capacitor, all hooked up to a power source. But this basic design is the backbone of almost every electronic device you own. So here's the big question. When we flip the switch, what exactly does the electric current do? Does it just jump up to full power instantly? Does it wiggle around a bit? How can we possibly know for sure?
To figure that out, your standard high school algebra just won't cut it. See, the current in this circuit isn't some fixed number. It's a living, breathing thing that changes from one microsecond to the next. To understand it, we need to describe the rules that govern how it changes. We need to speak its native tongue, the language of change.
And that language? Well, that's what differential equations are. They're these incredible mathematical models for anything that's dynamic and changing. The amazing thing is, instead of just solving for a single number, we get to solve for an entire story, a function that shows us exactly how something behaves over time.
Whoa, okay, I know. That looks pretty intimidating, right? But hang on, don't think of it as some scary formula. I want you to see it as a single, powerful sentence written in this language of change. This one line tells the entire story of our circuit. It's the complete blueprint for how that current is going to behave.
So let's translate that sentence piece by piece. It's actually pretty cool how it works. Each part of the equation is one of the components in our circuit. That L term, that's the inductor. It doesn't like change, so it resists any shifts in the current. The R term is our good old resistor, just providing a steady, constant pushback. The C term represents the capacitor, and its whole deal is storing up and releasing charge. And all of that action has to perfectly balance out with the juice coming from the power source, E of t. It's this beautiful marriage of physics and math, right there in one line.
So we have the blueprint, but what is the solution? The actual story of the current look like? Well, when we solve it, we find out it's a story that has two very different parts.
Yeah, it turns out the answer isn't just one simple curve. The total current is actually the sum of two completely different behaviors playing out at the exact same time. It's like two subplots that weave together to tell the complete story of the circuit's life right from the moment you hit the power.
This is where it gets really interesting. The current basically has a split personality. First, you've got the transient part. Think of this as the initial shock to the system. You flip the switch, and there's this brief moment of chaos as the circuit tries to figure out what's going on. It's the settling down phase, and it dies out pretty fast. But then, you have the steady state part. This is the long-term, stable, predictable behavior. It's what the current does once all the initial drama is over, and it's just humming along, powered by the source.
The source material really puts it perfectly. It says the current in an RLC circuit is composed of two distinct parts: the transient current, that diminishes to zero, and the steady-state current, which is sinusoidal and persists over time. So think about that. We solve one equation, and it predicts both the chaotic beginning and the stable, predictable future. That's incredible. And here's the real kicker. This whole idea, a solution made of a temporary part and a long-term part, it's not just some neat trick for circuits. This is a fundamental pattern, a core concept you see over and over again when you're speaking the language of change. It's a huge deal in solving all sorts of differential equations.
Okay, so let's zoom way, way out for a second. Because this language we've been talking about, it's not just for electronics. It's a code that helps us describe the entire cosmos.
So what's the official textbook definition? A differential equation is simply an equation that connects a function to its derivatives, its rates of change. Put simply, it's the most powerful tool humanity has ever invented for modeling anything that grows, shrinks, moves, or evolves over time.
And when I say it's powerful, I mean it's everywhere. The exact same kind of mathematical thinking that describes our little circuit also models how populations grow, how a hot cup of coffee cools down, how planets stay in orbit, how fast chemical reactions happen, even how stock market prices fluctuate, and how diseases spread through a society. It is, without a doubt, a universal code. But as powerful as this language is, there's a really important real-world twist. What happens when the problems get so messy, so complicated, that you just can't solve them with a pen and paper anymore? Because the hard truth is, as one of our sources points out, there exist quite a number of differential equations that cannot be solved analytically.
What this means is that for a ton of really important real-world problems, like modeling climate change or the chaotic flow of a river, a single, perfect, elegant formula just doesn't exist.
So what do we do? Well, scientists and engineers have two tools in their toolbox. There's the analytical solution. That's the beautiful, perfect formula we got for our simple circuit, the kind you can write down. But when that's not possible, we turn to the numerical solution. This is totally different. It's where we use a computer to generate a super accurate step-by-step approximation of the answer. It's not the exact formula, but it gets us incredibly close. Using these incredibly clever numerical methods, computers can chew through the numbers and predict the behavior of unbelievably complex systems, even without a neat little equation. This is exactly how we get modern weather forecasts. It's how engineers design airplanes and massive suspension bridges. This is the frontier, where massive computing power lets us unlock the secrets hidden in the language of change.
So, from a humble little circuit all the way up to the entire cosmos, differential equations give us this amazing framework for making sense of a world that is always in motion. They prove that even when things are constantly changing, there are deep underlying rules and patterns that we can understand and predict. So the final question really isn't just about what these equations can do, it's what mysteries will we solve next with the language of change.